Hello, everybody. We are at the end of chapter 8. Today is the last section in chapter 8. I just looked at it. Let me make sure because I just looked at the calendar. 8.2 is what is assigned today. And then we start into chapter 9 tomorrow, which is on confidence intervals. And then what you have left is hypothesis testing, and that's it in chapter 10. So really exciting to look that we're into the last couple of weeks of the class, and you've learned so much. And I know I said this before, but at the end of the class, end of the quarter, this whole class comes full circle. I have you research a scientific study, and most students tell me that that is just like the light bulb that turns so bright, and they're so excited about all the knowledge they've gained because they can interpret this study on a topic they're interested in. So you have that to look forward to. But right now we still have work to do, and I'm going to quit talking about that, share my screen. So the first thing that I want to do on is just kind of give you like a flow chart. I'll call it a flow chart. So a flow chart that has maybe the difference between the mean and the proportion, because you've been learning these sampling distributions. Sampling distribution for the mean is 8.1. Sampling distribution for proportion is 8.2. So knowing which one you have, there are characteristics of each distribution, and that once we recognize that, we're able to use the tools that we need. So just like binomial distribution, we had to check off the 4 characteristics: fixed number of trials, constant probability, 2 outcomes, and the independence. So those characteristics, before we could just jump in and grab StatCrunch and or calculator and come up with a probability, it's the same idea here. We have to check off these characteristics before we can use the tools. So if you're looking at my diagram here, sampling distribution, I have sampling mean. I've been talking a lot, so my voice is really kind of funky right now. Sampling mean, and we know that the sampling mean is X bar. If we take a sample proportion, we know that we use p hat to recognize that. Okay, if we have a sample mean, then we know that the mean follows a normal distribution. So the mean will follow this normal distribution if the population is normal. So it'll say the sample comes from a population that's normally distributed, or it'll say assume that the population is normally distributed. So if you're given that, then you don't need to check anything else. If you're not given that information about the population, then you need to check the sample size. And I tried to explain that I sent you out a quick video. Well, I guess it wasn't that quick because it was like 20 minutes. I want it to be quick, but it was a video that I did talk about that. It doesn't have to be both things. It just has to be one or the other. So if the population is normally distributed, it doesn't matter the sample size. If you don't know if it's normally distributed, then the sample size matters. Okay, enough of that. If you're looking at proportion, the way we can use a normal model is we first have to look at the sample size and check to see that it's smaller than 5% of the population size. And we have done this before when we were looking at proportion. So sample size needs to be, or when we were looking at binomial, that's where we saw it. So when we were looking at binomial, we were checking for independence. This was one way we could assume independence. Same idea here. The sample size is smaller than 5% of the population, we're good to go. But we also have to have the other requirement. So for proportion, for the normal model, both of these have to be satisfied. So you also need to check that n times p times 1 minus p is greater than or equal to 10. So the sample size times the population proportion times the 1 minus the population proportion, that has to be greater than 10. So I have between here the word and if you look over on X bar, it's the word or. So that's the difference between both of those, okay? So both requirements have to be met for proportion. But for normal, just one of those requirements has to be met. Okay, so if we can use the normal model, then we have these tools. So we know it follows a normal model, then we know that, we get here. So if X bar follows a normal model based on what we just talked about above, then we know that the mean of the sample means is the same as the population mean. The mean of the sample means is exactly the same as the population mean. The standard deviation of the sample means is going to be smaller because we take the population standard deviation sigma and we divide it by the square root of the sample size. So we know those are the parameters. I'll just use that word that we need to remember. So these are the parameters. The mu and the sigma, mu of X bar, sigma of X bar, that we can use in our model. For proportion, so we have to check that p-hat follows a normal model from what we did above. And then our mean and our standard deviation, the mean of the sample proportion is the same as the population proportion. So that's very similar to what we're doing with the mean. So the mean of the sample proportion is the same as the population proportion. And then the standard deviation of the sample proportion has to be calculated, the square root of p times 1 minus p over n. That has to be calculated. And then we can use the normal model. Okay, so those are just the parameters that we would use. Okay, so let's move on from there. Now, what I have uploaded, and I don't look at confidence intervals, so we're not there yet. What I have uploaded in the Zoom meeting should be the review of chapter 7 and chapter 8. Is that what's up there? Is it? And I think that's the only thing I put up there, right? Only one piece of paper, is that right, Crystal? Thank you. Okay, so that's what we're doing. I just wanted to make sure. I was working on this class last night and I had a couple ideas of direction I was going to go, but I'm going to stick with this direction. Okay, so chapter 7, I gave you a big video on the chocolate chips on chapter 7, but I still want to go over some of this. I want to jump into the last couple of problems first. So I want to go into problems number 5 and 6 instead. So I'm going to jump down into 5 and 6. Oh, I did it there. That's funny. Okay. So I do want to talk about the first 4, but I want to jump into 5 and 6 because we just looked at the distribution of the sample mean and the sample proportion. So let's first go here. Number 5. Okay, a machine used for filling plastic bottles with a soft drink has a known standard deviation of sigma equals 0.05 liters. The target mean filling volume is mu equal to 2.0 liters. Describe the sampling distribution of X bar, which is the sample mean fill volume, for a random sample of 45 such bottles. Okay, so describe the sampling distribution. So we're looking at X bar. Does it follow a normal distribution? So do we know that from the information given?
Yeah, because the deviation, never mind. Nope.
Yeah.
Nope. Because the deviation is 0.05? No.
Okay, so look what we did up here to find out if it's normal. So does it say anything about the population?
The sample size is over 30.
Yeah, correct. So in our problem, it doesn't say anything about the population being normal or the sample coming from a normal population, normal distribution population, but we do know the sample size is 45. So I encourage you to talk. It's all good. Okay. It follows a normal distribution because n is greater than 30. Well, let me write it this way. I'll say n equals 45, which is greater than 30. Okay, so because the sample size is large, we can assume the normal distribution. Now we need to calculate. So if we can assume the normal distribution, then we can talk about the parameters. Okay, so if I go back to that problem, we know that the mean was given, mu was given to be 2.0 liters, and the standard deviation was given to be 0.05 liters. So the mean is 2.0. I just said it and I can't remember what I said. 2.0 liters, and the standard deviation of the population is 0.5. 0.05. I didn't speak that right. So 500, 0.05 over the square root of 45. So I have to calculate, because I'm looking at the sampling distribution of X bar. So I'm using the standard deviation of the population divided by the square root of n. Okay, and we will just round this off 4 decimal places, 0.0075. So the sampling distribution of the mean is that it follows a normal distribution. The mean is 2.0, and the standard deviation of the mean, the sampling means, is 0.0075. Okay, so that answers part A. Okay, let's go to part B. The quality control manager obtains a random sample of 45 bottles. He will shut down the machine if the sample mean of these 45 bottles is less than 1.98 liters or greater than 2.02 liters. What is the probability that the quality control manager will shut down the machine even though machine is correctly calibrated? So he's going to shut it down if the sample mean is less than 1.9 liters or greater than 2.02 liters. Less than 1.98 liters or greater than 2.02 liters. So we're looking at the probability that X bar is less than 1.98 liters or the probability that the sample mean is greater than 2.02 liters. So that's what we're trying to find. Does that make sense? So
No, what I wrote it as the probability of 1.98 is less than X is less than 2.02. Is that the same thing?
It is the same, but we always write variable first. So it would be like, yeah, and it's just consistent to say that because we're talking about the value of the variable. So like the variable is less than 1.98.
Okay.
The variable is greater than 2.02.
Okay.
Technically, they're the same thing, but mathematically, just like when you write things in order from smallest to largest, that's just more something that's more mathematical. Okay, so now what I want to do is I want to draw my diagram. I understand what I'm trying to find. So I want to relate it to my graph. And remember that the mean, here's my sampling distribution. I just came up with it. X bar follows a normal distribution with 2.0 as the mean and 0.0075 as the standard deviation. So I know that the middle of my distribution is 2.0. And then I'm going to add 1 standard deviation. So 2.0075. I'm going to go out 3 standard deviations, which means or 2 standard deviations, sorry. So adding 1 more standard deviation, 2.0. Mhm. Okay. 2.0075 plus 0.0075, 2.015, and then one more standard deviation. So plus 0.0075, 2.0225. Okay, we're going to go the other direction. So from 2.0, I'm going to subtract 0.0075. And subtract again another standard deviation. And then one more. Okay, so I know that that takes time, but especially when you're doing your homework, do this because it's the visual that connects what you're doing. All right, so now let's shade what we are trying to find. X bar less than 1.98. So 1.98 is going to be over here somewhere. And I want less than that. So this is the area. 2.02 over here. And I want greater than that. So now I can see and understand what I'm trying to find visually on the graph. So I have my choice of TI-84 calculator or I have StatCrunch. And I also want to think about how I can get this in the quickest way. So if we could find the area here, if I found that area first, then I'm just looking in between 1.98 and 2.02. So if I find that area and I subtract from 1, I will get the tail ends. I want to do that because that's going to be quicker than finding the area of the left tail, finding the area of the right tail, and adding them together. So I'm going to find the area where the sample mean is between 1.98 and 2.02. Once I get that, I'm going to subtract from 1, but let's start there. So we can use our normal CDF from 1.98 up to 2.02. The mean is 2, the standard deviation is 0.0075. Okay, so second bars, normal CDF, 1.98, 2.02. Mean is 2, standard deviation 0.0075. And we get approximately 0.9923. We can go to StatCrunch. We go to Stat. We go to Calculator. We go to Normal. And we need to choose the one that says Between. So not the one that says Standard, but the tab at the top that says Between. That's what we're trying to find. So we choose the between one. And then at the bottom, we need to put in the mean, the standard deviation, and then you'll have your probability in between here you have to fill out. Those are all the boxes. Okay, so put in your 2.0, your 0.0075 for StatCrunch, your 1.98, your 2.02, and then you press your compute, and it gives you the answer right here. Okay, so that is how we got just the center. So if I stopped right now, I would get the wrong answer because I only found that what that center area is. But my goal is, what is the probability that the sample mean is less than 1.98 or more than 1.20? So now once I get my value, now I have to subtract. Now subtract from 1. So 1 minus 0.99, what was it again? 23, 9923. 0.0077. Okay, so the probability that the machine will get shut down. So what is the probability that the quality control manager will shut down the machine even though machine is correctly calibrated? The probability is 0.0077. Okay. All right, so now let's move on to, oops, I'm going the wrong direction. Here we go. Let's move on to number 6. Okay, so this, if you haven't done the homework for 8.2, this might be a little bit more confusing, but I think it's the same model as the sample mean. So we're just going to do the same process.
And I apologize. I actually will have to watch the rest of the video later. I wanted to catch as much of it as I could, but I have to go pick up my daughter. So, okay.
Drive safe.
Thank you.
Okay, so number 6, we're looking at the distribution of the sample proportion. According to the National Center for Health Statistics, 22.4% of adults are smokers. A random sample of 300 adults is obtained. Describe the sampling distribution of p-hat, which is the sampling proportion of adults who smoke. So we're going to go back up to our little diagram up here, and we know that we're looking at the sample proportion. So we need to check the normality, and we have to have both of these characteristics met. So the sample size has to be smaller than 5% of the population, and n times the population proportion times 1 minus p has to be greater than or equal to 10. If this fails, we would check the binomial distribution. So if these characteristics fails, you would go and check the 4 characteristics of a binomial, and then you might use your binomial tools to get the probability. Just a side note there. All right, so let's go back here to first page. Okay, so we're trying to find, does p-hat follow a normal? And we're going to check that the sample size is smaller than 5% of the population. So 300 was in the sample. Okay, so I'm going to go back to the problem again. We're looking at, according to National Center for Health Statistics, 22.4% of adults are smokers, a random sample of 300 adults. This is an assumption, but definitely a sample size of 300 is a lot smaller than 5% of all the population of adults. So we're checking that off. Okay, so yes, checks that off. So then the other one that we needed to verify, that's not how I wrote it. So it's n times p times 1 minus p has to be greater than or equal to 10. Your n is 300. Your p is what was given. So your p was the proportion of adults who are smokers. So this statistic here, 22.4%, it's actually your parameter. That's your p. It's not from the sample. It's just, it's a population proportion. It's not from the sample. So p is 22.4%. Which we know changes to a decimal 0.224. We have to write it in decimal form in order to calculate with it. Okay, so we get, when we multiply this out, we get 52.1472, which is definitely greater than 10. So we have met that characteristic as well. So now we know that my proportion follows a normal model. So now we need to look at the mean of the sample proportion. We know it's equal to p, so that's equal to 0.224. The other parameter is the standard deviation, which is the standard deviation of the sample proportion is the same as the square root of P times 1 minus P over N. So we need to calculate this. 0.224 times 1 minus 0.224, all divided by 300. So when you're putting this in your calculator, you choose your square root and then put the numerator in a parenthesis and then divide by the denominator of 300. And we should get approximately 0.02407. So we have come up with the sampling distribution of p hat to be a normal model with a mean of 0.224 and a standard deviation of 0.02407. And if you're asking me about round off, I could have taken it to 4 decimal places. I'm just trying to be, the more decimal places you carry it out to, the more accurate it's going to be. And if you're not rounding, then it's the most accurate. StatCrunch will tell you, or my stat lab homework will tell you how far to round off. So pay attention to what they tell you. Okay, so we did that. Now let's go back to the problem. Okay, so now we're on part B. In a sample of 300 adults, what is the probability that at least 50 are smokers? At least 50 are smokers. So we're looking at the probability at least 50 are smokers. Okay, so let's write that in this inequality. So it's p hat is my variable. No, I'm not working with x anymore. I'm not working with x bar. It's not a sample mean, it's a sample proportion. At least means greater than or equal to 50. So we're translating our words into symbols that are statistical symbols that are mathematically correct. Now we're going to take this and figure out what it means in my diagram. So in my diagram, it's a normal model, so that's why I'm drawing a bell-shaped curve. We verified it follows a normal model. The mean is the same as the mean of p hat is the same as the population proportion. So that was at 0.224. And then I'm going to round this just to draw my graph. So just to draw my graph, I'm going to round the standard deviation to 0.024. So I'm just going to add 0.024 to the 0.224. So 0.248. Got another standard deviation, add the 0.024, 0.272, and then 0.296. Subtracting the standard deviations to the left. 0.2, 0.176, 0.152. Okay, so just to give me a sense of where this is. Okay, now why is this so funky? Why is 50? It's really not a proportion, is it? So this is really not correct how I wrote that, because at least 50 is a number, it's a count, but it's not a proportion. So what I actually found was, I'm going to leave that up there just so you can see. I wanted the probability that X was at least 50. That's what I wanted. But I want that as a proportion. So I want P hat is greater than or equal to 50 out of 300. So I need to make sure that I'm writing this in terms of P hat and not a count of X. So 50 out of 300. Which is the probability of p hat greater than or equal to 1/6, which I'm going to use as the decimal just because I have my graph in decimal form. One divided by 6 is 0.1667. Let's say 1.67 here. Okay, so really important. to make sure that you are entering in a proportion and not just a count. This is how it kind of relates to the binomial too, is because you're counting the number of people who smoke. So that would be like your number of successes out of the number of trials. Your trials are your sample size of 300. So your p hat is 50 out of 300 or 1/6, and in decimal form 0.167. So I can plot that on my graph, 0.167. And I'm looking for more than. So I'm going to shade to the right. And then, they're going to use normal CDF with 0.167, infinity, put in the mean of 0.224, standard deviation of 0.024, what did we say it was? 2407. Okay, so second bars. As I've been reading your comments from the last Zoom meeting, some of you really like the option of the calculator because it tends to be pretty quick to just grab your calculator and instead of opening StatCrunch. But you can use either. Either are great. Okay. So we get approximately 0.9911. And then, of course, if you go into StatCrunch, you go to Stat, you go to Calculators, and you choose Normal. And then you will have the standard one. So you're going to choose standard, not between, because you just want standard. You're not looking at between two values. You're looking at the standard, which is we're just looking at greater than. So we're going to choose the standard calculator, and then you'll have your graph, and then you'll have the mean. And then you'll have standard deviation. And then you'll have the probability. And you'll put in the greater than. You'll put in 0.2 or 0.167 rather. And then you can choose compute. And I didn't fill these in yet, but this is 0.224 was the mean, and 0.02407 was the standard deviation. Okay, so one thing I don't like about StatCrunch, but I also like about it at the same time, is that you have to understand what the mean and the standard deviation you're looking for. We're talking about proportions here. So normally if we have mean and we're looking at the sample mean, the distribution of the sample mean, we would have this notation because we're looking at the mean of the sample proportions. StatCrunch is only going to have mu. It'll only have sigma. It's not going to have sigma and then the subscript to say, yeah, we're looking at this, the standard deviation. The other thing it doesn't have that. So that's not the correct variable because we're not looking at counting the number of X. We know this is really p hat. So you're using the tool of StatCrunch to get to the answer, but you have to interpret all of this. This part right here, it may not seem important and there's a lot of variables, but it's very important because it has to do with what you're understanding and the probability you're trying to find. We're looking at a proportion and not just a count. And that was exactly what had happened up here when I wrote p hat greater than or equal to 50. 50 is not a proportion. I had to create that proportion first and use the correct variables. So use your technology as a tool, absolutely, but really rely on that interpretation. That's the focus I've had in this class all along. Okay, let's see what else is there on this problem. Would it be unusual? So I'm back to part C in this problem. Would it be unusual if a random sample of 300 adults resulted in 18% or less being smokers, and why? Okay, here we go. Oh, that's the wrong problem. Let me get to the right problem. Okay, so here's my diagram. Getting my diagram.
Next one.
Thank you.
Next one.
Slide. Okay, here we're finally
There it
here.
is.
I need to use my, I have a different way to look at it. I should have looked at it there. Okay, so here's the diagram. I'm just going to erase some of this because my iPad can do that and it makes it easier than rewriting. Okay, so we're going to start out with the same graph. I'm going to erase all this too. But we want to look at the probability that p hat is less than 50. Less than, I just read my road. We want to look at the probability that it's less than 18%. Okay, so the probability that p hat, so now we have 18%. So if we have 18%, yes, we certainly can use p hat. We don't have to change it into proportion because that's what we're looking for. 18%, we can write that as a decimal, 0.118. So my 0.18 on my graph is about right here. And I want less than. So in my calculator, I still leave the 0.167. I don't want infinity. No, I need to change this because it's the wrong order. So in the order that I want it in the calculator would be negative infinity. So -1 E99 up to 0.18. And then we keep the the mean of the sample proportion and the standard deviation of the sample proportion. There we go. It's on second bars. I did already. Here we go. So this is going to be approximately 0.0338. And I'm not going to take you into StatCrunch. You know how to use StatCrunch again. But there's my probability. So if I'm asking if it's unusual, we would say, let me erase some of this stuff here. Okay, so let's interpret this probability. Since 0.0338 is smaller than 5%, then it is unusual. Unusual if a random sample of 300 adults results in 18% or less who are smokers. Okay, so those two problems represented 8.1 and 8.2. I tried to be very thorough and careful and try to give you some hints on your notation and how important that is. I'm going to go back to this worksheet, and number 1 through 4 is a review of chapter 7. So your next test is going to be on 7, 8, and 9. So review of chapter 7, a lot of it you already have learned, learned it so well that you're applying it to what we're doing right now. But let's go ahead and go to number 1, because this has to deal with reviewing the uniform distribution. Okay, so that's a different distribution than normal distribution. A uniform distribution looks like a square box, looks like a rectangle is the shape of that distribution. So a continuous random variable X is uniformly distributed, and it gives you where X is defined. X is defined between 10 and 50. Let's draw the graph of the uniform density function. Okay, X is between 10 and 50, and it's a uniform distribution. So X follows a uniform distribution. And we know that X is defined between 10 and 50. So if I'm going to draw the graph, okay, I know 10 to 50 is going to be my X. Okay, so I need to know the height of the rectangular box. We found this by looking at area. We know area is length times width. The entire area under a probability distribution curve or box, in this case, a rectangle, is always 1. So the total area is 1. If I call the distance from 10 to 50 my length, so I'm really just looking at this box where I have 10 as my length. I know my area equals 1, not 10. 10 is not your length. 10 to 50. So this is my length, and this is my width. So the distance from 10 to 50 is 40, right? 10 to 50, that's a distance of 40. But I don't know the height of the box. So I know in my formula, I could write the length is 40 and the width is my unknown. So when I divide by 40, I get 1 over 40 equals the width. So the height of the box is 1/40. So that's the probability. This is the probability density function. So this is your P of X. And then your y-axis is your probability and your x-axis is the count. Okay, so that's how we would draw the graph. Go back to the question. Draw a graph of the uniform density function. What is the probability that X is between 20 and 30? So we're reading that statement as what is the probability that X is between 20 and 30? So I'm going to go back to, this was A, so there's the graph of my function. Part B says, what is the probability that X is between 20 and 30? I'm going to use this same graph. I'm going to redraw it down here. And I'm going to shade. So the probability X is between 20, here's 20, here's 30, and I want the area. I know the area of a rectangle is length times width. I'm trying to find the area because that's the probability. So what is the distance of the length? I know the width is 1/40. That's the height of the box. So the height of the rectangle is the width. I'm calling that the width. So that's 1/40. And then the length is just the distance of 10. So between 20 and 30, that's a distance of 10. So the area is 10/40 or 1/4, or we can write that as a decimal 0.25. So the probability that X falls between 20 and 30 is 0.25 by using our knowledge of geometry with the area of a rectangle, because the area corresponds to the probability. We had to first find out what the height of that probability distribution is. So we had to come up with our uniform distribution first, and then we could use that to answer the question. Okay, let's go to part C now. Part C is, what is the probability that X is less than 15? X is less than 15. So I'm going to use my original diagram. Part C, probability that X is less than 15. I'm going to shade that in here. So 15 is between 10 and 20, and I want less than that. So I'm looking at the area of that box. So the area is what I'm trying to find. The length is the distance between 10 to 15, so that's the distance of 5. And the width is 1/40th. So if I take 5 times 1/40th, I get 5/40. I reduce that fraction to 1/8, or we could write it as an exact decimal, 0.125. All right, so that was a review of the uniform distribution. Let's see, what do we have time for? We're getting 32:30. Let's see. Okay, we might as well do this one too. Okay, number 2. Okay, I gave you a big discussion yesterday about not using z-scores. Well, if you're asked to find one, you have to find one, but usually we don't have to go outside and find the z-score and then wrap back around to the problem. But if you're asked to find one, yes, of course you need to.
No, it was just weird how the view an example button
I know.
through that and when
I
it wasn't necessary. And so,
I agree.
yeah, there were a couple people that struggled with that one. I was like, wow.
Every single quarter that happens. And I wish I could just like take that out, because we don't use that. They build it in for instructors that choose to always want you to calculate the z-score and go to a table instead of using technology, but it's really not helpful. So
Okay.
I was hoping, I'm glad that you asked me, because then I was able to remember I needed to really talk about that. And so I made that video to send it out to everybody. So
Yes, thank you.
you can skip that whole section. I know that helped me solve this, and that's what you all use a lot for help.
Yes.
And I think it's been good for the most part, but this is one part of it I wish that I could take out of it. But like you do, and like other students do as well, always contact me. Give me the heads up. Let me know what you're confused about, because it might be something like this that I really want to share with the whole class.
Okay.
So good job.
It was confusing. Yeah, thank you.
Good job for contacting me. Okay, so let's do number 2. Find the z-score that separates the middle 88% of the data from the area in the tails of the standard normal distribution. Okay, so we have a couple words here. Standard normal. So if it says standard normal, then we know that we're definitely talking about the distribution of the z-scores. So just with that word standard, that's what it indicates. And we want to know the z-scores that separate the middle 88%. So there's your middle 88%, and we're trying to find out what are these values on the number line, because really we're looking at values on the number line that separate the middle 88%. We also know if it's a z-score, then we know that the z-score follows a normal distribution with the mean of 0 and a standard deviation of 1. So I know the mean is 0. Okay, so how I find this is I can use my inverse norm on the calculator. And your inverse norm always wants the area to the left. So if I'm looking for the z-score on the left side here, I need to put in the area to the left of that. So I would have to think about, what is this area here? If you have 88%,
6%. 6%.
Yes, because 12% would be the tail. So this would be the 6% on this side and 6% on this side. So you'd have to put in 0.06, and you put in the mean and the standard deviation. So you get negative 1.55. On StatCrunch, you would just leave the area blank. Let me just remind you how to use StatCrunch. Okay, on StatCrunch, you would say, get a pen here. So StatCrunch, and you know, I'm not going to keep writing this, but stat calculator is normal. And then you would go into, it'll say mean and standard deviation. So choose 0 and 1. And then under here would be PX equals. So you would put in, we want less than. We don't know this number. This is what we don't know. So we're trying to find. But we know that the area to the left is 6%. Oh, we could do it from between. Actually, this is a fine way to do it. But we could easily, instead of using the standard, so that this would be if you choose the standard instead of the between. If we chose between, because this is only going to give us this one score. But if I use StatCrunch with the between, so if I use StatCrunch with the between instead of the standard, I think you all know what I'm talking about. So you're going to select this between. You would still do the mean and the standard deviation of 0 and 1. And then your commands will look like this. So you would, this is what we don't know. We don't know what these numbers are. But we know that the area is 0.88 between. So that would be the fastest way to do it, really. Because this would give you both areas or give you both Z-scores. And remember, this is what I don't like about StatCrunch, but it makes you think because you're looking at the probability of Z, not X. Your variable is Z, it's a specific distribution. So this would be definitely the fastest way to do it. But you can still use your calculator if you want to find one and then the other. This would be the fastest. Okay, I think that's probably enough for that problem. Let me see what else is left here. Find the value of, let's see, okay, let's do this one now. So this one is going to be very similar to.
Yeah, now we're going to go into Z sub alpha in chapter 9, correct? I believe Tony was saying that he was struggling a bit with it, yeah. So is this one going to be, you're going to show us how to do Z sub alpha.
Z sub alpha, alpha represents area to the right. So you will be using that with, because you would in the confidence intervals, you'll be introduced to critical values is what they're called. So Z sub alpha, where alpha equals the area to the right. Okay. Yes. All right. So area to the right would mean if I have Z sub 0.05, that means I'm looking for the Z score, and I don't think it's 0.05. Is it 0.06 on our sheet?
0.04.
Oh, 0.04. Okay, sorry. 0.04. 0.04. Okay, so you're on if you're looking at Z-scores, the standard normal distribution, 0 is in the middle. 0.04 means the area to the right is 4%. So that's 0.04, the area to the right. And you're trying to find what is the value, what is the Z-score, the location on the number line. That's what you're trying to find. So we could use StatCrunch. If we used inverse norm, we would have to put in the area to the left is what the calculator wants. So even though on your calculator, it'll say area, we have to know that it wants the total area to the left. That's how it computes it inside of the calculator. But Z sub alpha over Z sub 0.04 means the area to the right. What is the Z score? We're 4% of the areas to the right. If you use your StatCrunch, then you would go X, you would choose this. So you still would have mean and standard deviation 0 and 1, and then you would choose the greater than. Oops, I'm trying to get the right pen here. So you would choose the greater than symbol because you're looking at the area to the right of the z-score. This is your z sub alpha over, or z sub alpha. We don't know this, so this is what we want to find out. But we do know the area to the right is 4%. We would enter that in. Second bars, inverse, 0.04. So then we would get approximately 1.645. 64, that's fine. So if you, I mean, all of this, when you're using technology, technology again is a tool, but interpreting it is really important. If you put in your calculator, if you put in 0.04 instead of the 0.96 and you got a negative number, so if you got a negative, you know that you did something, you probably did it backwards, right? Because it's not negative, because if zero's in the middle, this is this direction is a positive value. So you would know, uh-oh, there's something wrong. So that also is just a reminder for you to be careful when you interpret. But yeah, the z sub alpha over 4, and I keep saying alpha over 4 because I'm so used to the critical value. We often look at alpha over 2. So ignore what I'm saying right now because that's later. What I want to say is z sub 0.04. So the 0.04 represents area to the right. So whenever you have a subscript here, it always represents area to the right.
Okay, thank you for that. Yeah.
Okay, I don't think we need to go over this last problem. It's already 2:30. It's because I just did the one with the chocolate chips. So I did that on the video. So it's very similar. I can here, I'll open this up right here. Let me see. Okay, so if you want to pause it, take a screenshot, there's the answers. Okay. So if you want to pause the video or take a screenshot, there's the answers for number 4. And I did it all with calculator on this one. So let me make it a little bit bigger. Can you see it all right? There we go.
Yep, I got it. Screenshot it.
Okay, perfect. Okay, so that will be if you want to check that your answers on that. But otherwise, I think that's good. Let me know if you have questions as always. And moving into confidence intervals, this is when it's getting exciting. Like the last, well, I think it's all exciting, but the last chapter in hypothesis testing, it brings everything together. And I wish we could spend so much more time. When I was teaching this on campus, I would have students do projects and presentations, and it was, I don't know, it was so good. And I missed that.
I think it would be easier in person for sure.
Yeah, in person's great, but at least we get Zoom. You know,
Yes.
I'm really excited that this is what I've been doing with my online classes, because I used to never see my students. We didn't have Zoom, you know, a couple of years ago, we didn't even have that.
No.
opportunity.
Nope.
So I think this is at least it's better.
It is good. Yes. Yes. Better. Yes. That's a good word for it. Well, thank you so much. I appreciate it.
Yeah, you're welcome. I'll talk to you soon.
Okay. Bye.
Bye.